Welcome to the deep dive.
It's fantastic to be here.
We spend a lot of time on this show talking about the what of AI, what can it do, what are the new models, what are the ethical implications,
The big picture stuff.
the big picture, exactly. But today, I want to roll up our sleeves and really get under the hood. We are going to look at the engine block of the modern AI revolution.
We're going to perform a bit of brain surgery on the large language model.
Yes, exactly that. We are talking about attention. If you've been following AI at all for, the last decade, you know this word.
You can't escape it.
It's the mechanism that powers everything. ChatGPT, Claude, Gemini, it all goes back to that attention concept.
It really is the concept that changed the world. That famous paper from 2017, Attention is All You Need, essentially threw out the old rulebook.
Right.
It just said, this one mechanism. This is the key. It's the engine that drives the entire transformer architecture.
Right. And I feel like most of us, myself included, have this very specific, very confident mental model of what attention actually is. We've been taught to think of it like a database search.
The retrieval metaphor, it's very intuitive.
It is. So let's just walk through that standard view for a second, just to set the stage. I imagine the model is, reading a sentence. It gets to a word, let's say bank.
Okay.
That word is the query. It wants to know what bank means in this context. So it turns around and looks at all the previous words in the sentence. Those previous words are the keys.
Correct. It scans the history.
And it compares its query to all those keys. It's asking, do you match? Do you match? And it finds the best one. Maybe the word river appeared a few sentences earlier. So it knows, bank means river bank, not money bank. And then it grabs the information associated with river, the value, and pulls it in.
And that informs its next step.
It's a lookup. It's like a Google search happening inside the brain of the AI.
That is the classic intuitive explanation. And it's a good one. It's a content-addressable memory system. You shout a question the query into the void of the past, and the relevant pieces of information shout back based on how well they match. It's fundamentally a probabilistic view. What is the probability that this word relates to that word?
It makes perfect sense. It's clean, it's intuitive, but today we are going to completely shatter that view.
We are indeed. We're going to make the case that while that metaphor is really helpful for beginners, it might actually be mathematically misleading.
And worse than misleading.
And worse, it might actually be holding back the development of better, more powerful architectures.
So that's our deep dive today. We are digging into a fascinating new paper titled HyperMLP, an integrated perspective for sequence modeling.
This is by Jiecheng and Shihao, just released in 2026.
And the central question this paper poses is, honestly, it's kind of mind-bending. They ask, what if attention isn't a search engine at all?
What if it's a dynamic neural network?
Exactly. What if, instead of this nice, clean, probabilistic lookup, attention is actually a dynamic neural network that builds itself on the fly?
It's a radical shift in perspective. It suggests that we shouldn't look at attention as retrieving memories. We should look at it as constructing a circuit.
Okay, so we're moving from attention as lookup to attention as a dynamic MLP. Okay. Let's unpack this. Before we get into the heavy machinery of HyperMLP, and we will get into the geometry and the math set the stage for us, where are we in the world of AI that necessitates this kind of rethink? Why are we trying to fix what isn't broken?
Well, that's the thing. It is sort of breaking, or at least it's showing its age. If we look at the landscape, transformers are dominating everything. Language, vision, speech. It's all self-attention all the time.
The king of the hill.
Absolutely.
Yeah.
But we're starting to hit a wall that's known as the scaling laws.
The scaling laws, okay? This is the idea that if we just make the model bigger, add more layers, and just, dump more data in, it automatically gets smarter, right?
That has been the dogma for the last few years. The bigger is better era. Just throw more compute at it. But what we're seeing in recent industrial practice is that the marginal returns on simply scaling up are getting harder and harder to sustain.
So you have to spend exponentially more money.
And burn exponentially more energy just to get these tiny linear improvements in intelligence.
The brute force approach is reaching a point of diminishing returns. The well is running dry.
Exactly. We are seeing a saturation point. And this has forced the research community to kind of split into two camps to solve it. Camp one is focused on efficiency.
Efficiency. I assume that means making things cheaper and faster.
Yes.
Yeah.
This is where you see all the research into things like subquadratic attention, linear attention,
Right.
or these new architectures like Mamba.
Right.
They all want to process really long documents without computational cost completely blowing up.
Right.
But usually when you make something cheaper in this way, there's a trade-off.
There's always a catch.
And the catch is expressivity. Usually to make the model faster, you have to restrict what it can look at, or you compress the memory so much that you lose crucial details. You basically make the model a little bit dumber to make it run a lot faster.
So you take away its ability to look at everything perfectly so it runs smoothly, but maybe it misses the really important nuance buried in the text.
Precisely. Now, this paper, HyperMLP, takes the complete opposite approach. They are not in the efficiency camp. They are firmly in the expressivity camp. They are asking, how do we make the attention block smarter within the exact same computational budget?
I love that. It's not about cutting corners. It's about better engineering. It's asking, can we squeeze more intelligence out of the same number of parameters?
Precisely. Instead of just trying to make it cheap, how do we make every single parameter count for more? And to do that, they realized they had to fundamentally deconstruct the attention as lookup paradigm.
They had to go back to first principles.
They had to prove that the way we've all been thinking about the math, that whole database view, was actually limiting what the math could really do.
Okay, so let's dive right into that deconstruction. This is the core thesis of the paper. They want us to stop looking at attention scores as probabilities.
This is a crucial distinction, and it's where everything else follows from. In standard attention, the process ends with a function called softmax.
Softmax. We hear this term all the time. Can you break it down for the non-mathematician?
Sure. Softmax is a function that takes a list of raw numbers, these are the attention scores, and it squishes them all so that they add up to exactly 1.0.
So 100%.
100%. It creates a pie chart. It forces the model to allocate a budget of attention.
A probability distribution.
Exactly.
Right.
And because everything has to sum to 100%, it forces a competition. If I decide to pay 90% of my attention to the word apple, I only have 10% left to distribute among all the other thousands of words in the document.
It's a zero-sum game. If I care more about one thing, I must care less about something else.
Correct. And the authors of HyperMLP argue that this is actually restrictive. They call it the probability cage. Why should the model be forced to choose?
Right.
What if 5 different things in the past are all equally important and all require high activation? Softmax forces you to dilute the signal. You can't give 5 things 90% attention.
That makes a lot of sense. So they propose an integrated perspective. They argue that if you just take away the softmax,
If you remove that final squishing function,
an autoregressive attention head looks exactly like a dynamic 2-layer MLP.
an MLP, a
Yeah.
multi-layer perceptron. This is, Deep Learning 101 speak for a standard feed-forward neural network.
His simplest building block.
Layers of neurons connected to each other, the bread and butter of AI.
But wait a second, a neural network, an MLP, usually has fixed weights. We train it for months, the weights are set in stone, and then we run data through it. You're saying here that attention is a neural network where, the weights change with every single word.
This is the aha moment of the paper. This is the core insight. The weights of this MLP aren't fixed. They are instantiated from the context history.
Instantiated.
Created, generated. The context, the words you have just read, actually creates the weight matrix for the network that processes the very next word.
Whoa, okay, so let me see if I get this. Normally I have a brain, a fixed structure, and I feed data into it.
Right.
Here, the data builds the brain that processes the next piece of data.
That is exactly it. It's a profound shift. The keys, the history form the weights of the first layer of this dynamic MLP, and the values form the weights of the second layer.
Okay, let's walk through the mechanics of this attention as MLP view then. In the traditional view, we had query, key, and value. We compared the query and key to get a score.
Right, a similarity score.
In the HyperMLP view, that calculation, the query times the key transpose, the famous QK Tala, is not a comparison. What is it?
It is the first layer of a neural network. It takes the input, the query, and it projects it into a hidden representation.
A hidden layer, like the middle layer of a normal neural net.
Yes. And think about the dimensions here for a second. This is what makes it dynamic. If you have read 1,000 words, that hidden layer is 1,000 units wide.
Okay.
But if you've read 10,000 words, it's now 10,000 units wide. It grows with the context.
So it is an ever-growing hidden layer. As I read more, my capacity to represent complexity actually increases.
Precisely. And then the value matrix, the dollars from the original paper, acts as the second layer of weights. It takes that massive hidden representation and projects it back down to the output size the model needs.
So instead of retrieving information like a librarian finding a book,
You're not retrieving.
you are activating a specific subnetwork based on the input. You're lighting up a pathway through this dynamically created brain.
It is a subtle but incredibly powerful shift in perspective. It means we aren't just picking a winner from a lineup. We're activating a complex pattern.
And this brings us right back to the softmax issue. If it's a neural network, you don't use softmax in the middle of a neural network, do you? That's not what we do.
Typically, no. You use what's called an activation function. And the authors of HyperMLP have a strong preference here. They champion ReLU.
The rectified linear unit.
Yep.
So why is ReLU better than softmax in this new context?
Well, softmax, as we said, forces competition. It lies on a simplex mathematically. Everything has to add up to 1. But ReLU operates in a cone. It's independent.
How so?
ReLU just asks a very, very simple question for every single neuron in that hidden layer. Is this value positive?
Just a yes-no switch, an on-off gate.
Exactly. If yes, keep the value as it is. If no, turn it off completely. Set it to 0. It acts as a gate. It allows the model to select specific slots in its memory to be active or inactive without caring one bit about what the other slots are doing.
Okay, so let me try an analogy. With softmax, if I really need to focus on tree, I have to ignore pi. With ReLU, I can say tree is important, and pi is important, and orchard is also important, and I can just keep them all active at full string.
Exactly. You remove the artificial constraints of the probability cage. This allows for what the paper calls input condition selection. The input itself determines which parts of this massive context-created memory pool are actually relevant. It's like it carves out a subnetwork from the history on the fly.
The paper mentions this 3-stage memory concept. I found this really helpful to visualize what's happening. Can you walk us through that?
Yes, it's a beautiful framework for understanding this instantiated brain idea. So stage 1 is the global memory space.
Okay.
This is defined by the model's static parameters, the things it learned during those months of training on a supercomputer. This is the raw potential.
The vocabulary, the grammar rules, the general knowledge about the world.
Exactly. It is the potential of what the model can understand. Then stage 2 is the context instantiated memory pool. As you process a specific document, say this research paper, the context creates these specific memory slots. This pool grows as you read.
Okay, so this is that ever-growing hidden layer we talked about. The specific book I'm reading right now is building this custom memory pool for me.
Correct. And finally, stage 3 is the current step activated memory. This is the subset of that pool that actually passes through the ReLU gate right now for the specific token you're trying to predict.
I see. So it's a funnel. It goes from universal knowledge down to specific document context, and then finally down to what matters right now.
And ReLU is the gatekeeper for that final crucial step. It decides what makes the cut.
Okay, so we've reframed the problem. Attention isn't a search engine. It's a dynamic neural network with an ever-growing hidden layer, gated by ReLU. That sounds incredibly cool, but, simply renaming things doesn't automatically make them better.
That's true. It's not just a rebranding exercise.
So the paper introduces HyperMLP as the architecture that actually takes advantage of this new view. And to explain why their architecture is superior, they start by referencing a classic essay, The Bitter Lesson by Rich Sutton.
Ah, yes. The Bitter Lesson. It's required reading in AI philosophy, really.
For those who might not have read it, what's the gist of The Bitter Lesson?
Rich Sutton, one of the godfathers of reinforcement learning, he argued that over the long arc of AI history, the only methods that truly win out are the ones that leverage computation. Things like search and learning.
Okay.
Whenever we humans try to hand-design features, like telling a computer, look for corners and edges to find a square, we eventually lose. The general method that just learns from massive amounts of data always wins in the end because it scales with compute.
So don't try to be too clever. Let the compute do the heavy lifting.
Basically. Now, the authors of HyperMLP argue that standard attention has a flaw that, in a subtle way, violates the spirit of the bitter lesson. It relies on a fixed positional basis.
What does that mean, a fixed positional basis?
It means when the standard model looks back at its history, it looks at the tokens exactly as they came in. Token 1 is here, token 2 is there. It treats the history as this rigid, ordered list of snapshots in time.
So it can't really mix information across time before the attention step.
Exactly. It takes the history as a fixed lineup of individual players. It can't say, well, the important thing isn't player 1 or player 2, but the interaction between player 1 and player 2. It has to infer that later.
The key itself is just the snapshot of that one token at that one point in time.
Right. And HyperMLP asks a very powerful question. Why are we treating the sequence as a fixed list? Why don't we learn how to mix the sequence slots themselves?
And this is the sequence mixing concept. This seems to be the absolute secret sauce of HyperMLP.
It is. This is the big architectural innovation. Instead of just mixing features like saying this vector represents a noun, HyperMLP learns how to mix the sequence slots.
So it's not just operating on the meaning of the words, it's operating on their position and relationship in time.
Yes. It might learn that to predict the current word, it shouldn't just look at the word 5 steps back. It should look at, say, a weighted average of the word 5 steps back and the word 6 steps back.
So it can kind of blur the timeline in a learned way.
In a structured, learned way, yes. It creates what the paper calls context-wide slots. Instead of each memory slot corresponding to one token from the past, a memory slot becomes a learned linear combination of the entire history.
Wow.
It's building better features on the fly. It's creating these super tokens that can represent concepts that span across multiple points in time.
Okay, that sounds incredibly powerful, but managing time in a neural network is notoriously tricky, especially when the text keeps getting longer and longer. The paper gets really technical about something called the lag layout or reverse offset layout.
This is a crucial engineering detail.
Yeah.
It sounds small, but if you don't get this part right, the whole sequence mixing idea completely falls apart.
Why is that? What's the problem it's solving?
Think about autoregressive generation, like when GPT is writing a story, predicting the next word. The task is always growing.
Right.
If you index things the normal way, token 1 is the first word, token 2 is the second, and so on, then the index of the most recent word keeps changing. First it's index 10, then it's index 11, then it's index 1000.
Right. It's a moving target. If I learn a rule that says, look at the most recent word, I can't express that easily as a fixed operation if the index of that word keeps shifting around.
Exactly.
Yeah.
Your learned operations would have to constantly adapt to the growing context length, which is a nightmare. So HyperMLP flips this on its head. It uses a lag layout.
Okay.
In the lag layout, index 1 is always the most recent token, index 2 is always the one before that, index 3 is the one before that, and so on.
So relative to now, the indexing is constant. Now is always position 1. The previous moment is always position 2. It's a relative coordinate system.
Precisely. It anchors the entire reference frame to the present moment. And the paper proves a really important theorem about this. They show that this layout ensures extension consistency.
Extension consistency. That sounds like a heavy math term. What's the intuition?
The intuition is that the math remains stable as the context grows. If you add more history, way back in the far past, like if you suddenly remember something that happened a year ago, it shouldn't break the math of what you were doing right now.
You don't want your brain to crash just because your memory got longer.
Right. The lag layout ensures that the sequence mixing operations you learned on short sequences still apply perfectly and mathematically when the sequence gets really, really long. It aligns the canonical extension of the math with the autoregressive truncation of reality.
That makes a ton of sense. It respects the arrow of time in a way that standard indexing doesn't.
Exactly. It's a very elegant solution to a very tricky problem.
Okay, so we are mixing the sequence, which is powerful. But mixing things usually means huge matrices. If I have a sequence of, say, 10,000 words, a matrix that mixes all of them against all of them it's gigantic.
It would be $10,000 times $10,000. That's 100 million parameters. Just for one mixing operation in one head in one layer. It's way too expensive. You would blow up your memory instantly.
So how do they solve this? They mentioned something called DPLR.
Diagonal plus low rank. This is the clever trick to making this whole scheme affordable. They realize they don't need a full, dense 100 million parameter matrix. They can approximate the mixing they need using two much, much cheaper components.
Okay, break those two components down for us. What's the diagonal part?
First, a diagonal matrix. A diagonal matrix is very simple. It only has numbers on its main diagonal and zeros everywhere else. All it can do is scale the individual elements.
So it can say, make this token louder, make that token quieter.
Exactly. It captures the local weight or importance of each individual token. It's very, very cheap computationally.
And the low rank part, what does that do?
Low rank is a mathematical way of saying compressed. Instead of a full grid of numbers, you represent the interaction with two very thin, skinny matrices multiplied together. This structure can't capture every possible interaction, but it's very good at capturing broad, structured patterns.
Like what kind of patterns?
Things like shifting data moving information from position 5 to position 6, or averaging local neighbors like a convolution. It can learn these complex mixing patterns without needing a parameter for every single interaction.
So you get the complexity of mixing the ability to smear data across time, but without the insane explosion in parameter count?
Exactly. You get the expressivity of a big, powerful matrix, but with the memory cost of a very small one. It's the best of both worlds.
And this leads to a really counterintuitive budgeting decision they made in the paper. Usually in transformers, we think the query and key matrices, the QK part, are the most important.
Right. That's the routing. That's the search engine part of the old metaphor.
And in standard attention, we invest a lot of parameters there. We give it a high dimension because we think finding the right information is the hardest part of the problem.
That's the common wisdom.
But the HyperMLP authors, actually, they shrink the QK rank. They make that routing layer smaller.
They do. They reduce the dimension of the query and key vectors pretty significantly compared to standard models.
Wait, so they make the search engine worse. Why would they do that?
Well, they'd argue they're not making it worse, they're making it more efficient. They make the dimension of the search space smaller. But they take those saved parameters and they keep the value output, VO, rank very high.
Okay, what's the logic there? Why shrink the routing and fatten the content?
It goes right back to that dynamic MLP view.
Mm-hmm.
Remember, the first layer, the QK interaction, creates the hidden representation. Its job is essentially to decide which neurons to turn on. It is a routing layer.
It's just the switchboard operator.
It's the switchboard. And you don't need a massive high-dimensional space to simply make a selection decision. A smaller space can be just fine for pointing.
Okay.
But the second layer, the value output layer, that's the action layer. It's what actually updates the hidden state of the model. It carries the real information content, the definitions of words, the concepts, the relationships.
The substance.
The substance. So they argue, we need high fidelity in the content, the VO, but we can afford a lower fidelity in the switchboard, the QK, especially since we've now added sequence mixing.
Because the sequence mixing makes the routing itself smarter.
Exactly. It's better to have smart, flexible routing over a smaller space than to have dumb, rigid routing over a huge space.
That is a fascinating trade-off. It completely challenges the default settings that, everyone has been using in transformers for years.
It really is.
It suggests we've been over-investing in the addressing system and under-investing in the content system this whole time.
It's a total rethink of the entire allocation of resources within the attention block.
Okay, this is a perfect transition. Let's move to part 3, the theoretical implications. This is where the paper gets into the geometry of it all. And I know, listeners, geometry of high-dimensional space can sound intimidating, but the analogies here are just beautiful.
This is one of my favorite parts of the paper. It really explains why this sequence mixing idea matters so much from a mathematical first principles perspective.
They compare standard attention to HyperMLP using these two fantastic terms: polyhedral routing versus warped routing. Let's start with the standard one, polyhedral.
Okay, so imagine the space of all possible inputs to the model as a giant high-dimensional room. Standard ReLU attention makes its decisions by cutting this room with perfectly straight walls.
Hyperplanes.
Exactly, hyperplanes. It draws a straight line and says, everything on the left of this wall is irrelevant, I'm setting it to 0. Everything on the right is relevant, I'm keeping it.
So it makes straight cuts. Like cutting a gemstone, you get these flat facets?
Yes, a polyhedron. That's what standard attention creates. The boundaries of what it can think about are always composed of these straight lines.
And HyperMLP, what's warped routing?
HyperMLP, because it mixes the sequence based on the input before it hits that ReLU gate, it introduces a critical nonlinearity into the decision boundary itself. Mathematically, this bends the walls.
So instead of straight cuts,
it creates curved hypersurfaces, things that look like splines or curved surfaces.
The analogy I came up with while I was reading this was standard attention cuts the data with a knife. It can only make straight cuts.
Okay, I like that.
HyperMLP can scoop out the data with a spoon.
That is actually a very, very apt analogy.
I try.
Because it can curve the boundary. It can create acceptance regions that are shaped like spheres or ellipsoids or kidney beans, shapes that are fundamentally curved. And this is crucial for a capability called fuzzy recall.
Fuzzy recall. Is that like when I vaguely remember a song lyric but not the exact words? I know it's something like this.
Exactly. Sometimes you want to retrieve a memory, not because it's an exact match, which a straight cut is good for, but because it's close in distance. Geometrically, closeness is defined by a radius from a central point. It's a sphere.
And a sphere is curved. A knife can't cut out a perfect sphere.
Right. Standard attention really struggles to represent a sphere because you need an infinite number of tiny straight cuts to approximate a curve. It's like trying to build a perfect ball out of flat pieces of cardboard. It's incredibly inefficient.
But HyperMLP gets the curve for free.
It gets the curve for free because of that input-dependent sequence mixing deformation.
So this allows for what the paper calls strictly richer function classes.
Yes. This is the key theoretical takeaway. There are thoughts, mathematical concepts, and relationships that HyperMLP can represent perfectly and efficiently that standard attention simply cannot, no matter how much data you give it or how long you train it.
That seems huge. If the model's brain literally can't form a certain shape of thought, then no amount of data is ever going to fix it. HyperMLP is giving it a more flexible brain geometry.
Correct. It expands the fundamental geometry of thought available to the model.
There was another really cool detail in the theory section about registers. We've heard about vision transformers needing these register tokens, basically empty tokens to dump useless information.
Yes, the trash can tokens or scratch pad tokens.
But here they say HyperMLP uses these registers in a much more active, intelligent way. How so?
In standard attention, if there's a lot of noise in the input, say a bunch of random punctuation or irrelevant words, the model still has to attend to something, so it often just learns to dump its attention on these dummy register tokens, just to park it somewhere.
It's basically idling. It's putting the attention in neutral.
Exactly. But in HyperMLP, because of the sequence mixing, the model can do something much more sophisticated. It can actively sweep that noise together. It can learn to aggregate all the noisy tokens into a single dummy slot before the gating even happens.
So it takes out the trash automatically. It bags it all up.
It bags it all up into one place, and then the ReLU gate just shuts that entire slot off. It completely filters out the noise, which effectively increases the signal-to-noise ratio, SNR, for the actual meaningful slots.
That's another really powerful benefit of being able to mix the sequence before you process it.
It's a huge advantage for dealing with real-world messy data.
Okay, let's talk about HyperGLU. We've spent this whole time talking about HyperMLP, which uses the ReLU activation function. But the paper's best performing model is actually a variant called HyperGLU. What is the difference?
It comes down to a subtle limitation of ReLU. We said ReLU is great because it's independent and doesn't force that zero-sum competition. But it does have a quirk. In ReLU, the selection, the decision of should I pass this information and the magnitude, how loud is this signal, are coupled together.
Coupled how?
If the input value is 5, it is selected because it's positive, and it has a strength of 5. If the value is -5, it is not selected at all. You cannot have a value that is selected but very, very quiet.
You can't whisper through an open door. If you want the door open, you have to shout.
That's a perfect way to put it. You have to shout to open the door.
And that seems limiting. Sometimes I want to pay attention to a very subtle detail.
Exactly. HyperGLU solves this by splitting the path. It uses a gated linear unit, or GLU. Path A is the gate. It's a sigmoid function that outputs a value between 0 and 1. It decides if the information passes. It's the bouncer at the door.
Okay.
Path B is the scale. It's a linear path that determines how strong the signal is. It's the volume knob.
So it separates the bouncer from the volume knob. The bouncer decides if you get in, and the volume knob decides how loud you can be once you're inside.
Perfect analogy. The bouncer can say, you can come in, and the volume knob can say, but keep it down to a whisper. Or, you can come in and scream your head off.
And this gives the model more fine-grained control.
Much more. It offers much smoother optimization and better control for the model, especially during training. It allows for more nuanced gradients to flow back through the network.
Does this make it slower? We're adding paths, splitting things up. It sounds more complicated.
A little bit, but not in the way that changes the big picture complexity. The analysis in the paper shows it still preserves the quadratic scaling of attention.
So it doesn't fix the core N$2 problem of attention.
Remember, that was never the goal here. This is about expressivity, not asymptotic efficiency. But the overhead is just linear in terms of that low rank factor we talked about earlier.
The Doe term.
Right. And since that rank, theoreticals is usually small, like 16 or 32. The overhead is pretty negligible compared to the massive matrix multiplications that are happening elsewhere in the model anyway.
But they do mention a practical catch, and this is the elephant in the room for any new attention mechanism. Flash attention.
Ah, yes, the great optimizer. Flash attention is a highly optimized hardware kernel that makes standard attention just scream on NVIDIA GPUs. Yeah. It's a huge part of the reason why models like ChatGPT are so fast in practice.
But HyperMLP can't use it.
Not out of the box, no. Because HyperMLP fundamentally changes the math. It inserts that mixing step. It uses the lag layout. You can't just plug in the standard flash attention kernel and have it work. You need to write new custom kernels for it.
So it's algorithmically efficient, the math is good, and the complexity is sound, but from an engineering perspective, it needs some catch-up time.
Exactly. The authors provide what they call a block-wise implementation that makes it practically efficient enough to train and test their models, but it hasn't yet reached the bare metal hardware optimization levels of standard attention. That will come with time and adoption.
Okay, so we have the theory, we have the architecture, we have the geometry. But as they say, the proof is in the pudding. Let's talk about part 5. The empirical results. Does this thing actually work in the real world?
It does. And they were very thorough in how they tested it. They started with a controlled design study. They took a standard model and they swapped out different parts one by one to see what actually matters.
I love these kinds of ablations. So what did they find?
Finding number 1, and this is a big one, softmax is not essential.
The sacred cow of attention.
You can slaughter it. Their study showed that a well-tuned ReLU attention, even without any of the fancy sequence mixing, performs similarly to, and sometimes even better than, standard softmax attention.
So that whole probability view really isn't the magic sauce we thought it was.
It's not. And finding number 2?
What's that?
Sequence mixing is the game changer. When they added the mixing, the DPLR part that makes it a true HyperMLP, it consistently and significantly outperformed both the softmax and the simple ReLU baselines, all on the same parameter budget.
They tested this on the MAD benchmark. This stands for Mechanistic Architecture Design. It's like a gym for AI models to test very specific skills, right?
Exactly. These aren't broad knowledge tests. They are synthetic tasks designed to probe and break models. They test specific cognitive capabilities. And HyperMLP just shown on a task called noisy and context recall.
That's finding the needle in the haystack when the haystack is full of other fake needles.
A perfect description. Standard models often get confused by all the distractor noise. But HyperMLP, thanks to that register noise filtering capability we discussed earlier, was just able to ignore the garbage and find the signal much more reliably.
It also crushed a task called selective copying.
This is a fascinating task. It asks the model to do something that sounds simple to us. It'll say, copy the word that appears after the word apple.
So if the text says an apple pie is delicious and the prompt says what came after apple, the answer is pie.
Right. And standard attention really struggles with this because it's good at looking at apple, but it doesn't have a built-in concept of the thing immediately after apple. It doesn't know how to shift its gaze one step to the right.
It's a relative positional task.
But HyperMLP, with its lag operators and its learnable sequence mixing, can actually learn a shift operator. It effectively learns the concept of next as a geometric transformation on the sequence.
That is so cool. It learns the concept of next as an actual mathematical operation.
Precisely. It's a capability that emerges naturally from the architecture.
And then, of course, they did the big test, real language modeling. Synthetic tasks are fun, but can it write poetry? Can it code? They trained models on OpenWeb Text 2 and the new FineWeb ADO dataset.
Real text, real scale. They compared HyperMLP and HyperGLU against some very strong, very recent baselines models like RetNet, GLA, which stands for Gated Linear Attention, and of course standard softmax transformers.
And what was the final verdict?
HyperGLU achieved the best aggregate ranking across a whole suite of general ability benchmarks like MMLU Pro, which tests expert-level knowledge, GPQA for graduate-level questions, and the math benchmark. At the 1.3 billion parameter scale, it was the clear winner.
That is really significant, especially beating out models like RetNet and GLA, which are kind of the new hotness in the efficient attention space.
It completely proves their thesis. Investing in expressivity, making the attention head smarter, pays real dividends. You don't just have to chase asymptotic efficiency. You can actually build a better brain.
So let's bring it all together as we wrap up. We are really seeing a fundamental shift here. We are moving from a probabilistic lookup era, where we think of attention as searching a database, to a dynamic circuit era.
That is the headline for this whole deep dive. HyperMLP isn't just a small tweak. It's a complete redefinition of the primitive. The attention head is a two-layer MLP.
The context creates the weights.
And the input gates the subnetwork.
And critically, it aligns the math with the reality of time via that brilliant lag layout.
It is extension consistent. It respects the fundamental autoregressive flow of time.
Okay, so here's my final provocative thought for you and for our listeners, and I want to get your take on this. The paper proves that this sequence mixing allows the model to build these context-wide slots. It's not looking at individual tokens anymore, it's looking at these mixed, blurred concepts, and it creates these warped geometry, these curved decision boundaries.
Yes, all true. Where are you going with this?
If we are moving from rigid search and straight-line decisions to these fluid, warped, dynamic constructions that are built by the data itself, are we witnessing the evolution of attention from a search engine into something that looks a lot more like neural plasticity?
That is a profound way to put it.
I mean, in the human brain, synapses strengthen and weaken based on activity. That's how we learn. Here, the synapses of the attention head are literally instantiated by the context on the fly for every single step. The lookup is gone, the dynamic construction has arrived. It just feels more biological.
It really does. It suggests that memory isn't a place you go to find things. Memory is a process of reconstruction. And HyperMLP, in its own way, models that reconstruction mathematically. It's less like a computer hard drive and more like a dream that slowly stabilizes into a fact.
A dream that stabilizes into a fact. I love that. And we will leave you with that image to mull over. This has been a deep dive into HyperMLP.
Thank you for listening.
Thanks, everyone. We'll see you next time.